Hello everyone. Today in this video I'll be explaining you how to derive the expression for fringe width in Young's double slit experiment. For this experiment, S is the source of light, which is a primary source. S1 and S2 are the sources which act as coherent sources which emits the secondary wavelets. Suppose that these two waves are reaching or superimposing each other at the point P on a screen which is placed at a distance d from the secondary source, capital D. The distance between the two sources is taken as small d. Now, these two waves can superimpose each other at any point on the screen. But I suppose that it is reaching a point P. Now we don't know whether at the point P there would be a maxima or a minima. So we'll impose the condition of both and then find the expression for fringe width. For that, the central fringe, since at the center point on the screen, the wavelets reach in the same phase. Hence, at the center point of the screen, you will have a central maxima. It's a central fringe which would be the maximum. It would always be the brightest. Now, at the successive points, you have got a maxima and then a minima. This is a maxima again, this is a minima, again a maxima. Similarly, on the other side of the screen. Now, what is meant by fringe width? Fringe width is the distance between two successive maxima or minima. Like this is a maxima, this is a maxima. The distance between the two is called as fringe width. Similarly, this is a minima, this is a minima. The distance between the two is known as fringe width. So, our task is to find the expression. For that, I'll take up the path difference between the two waves. Now see children, here S1P and S2P are the waves which are reaching at the point P. Now I'll just show it here. This is S1P and this is S2P. Right? This is S2P. Now suppose that this is a wave which is reaching at this point. This is the waves from this point are reaching like this. Now, see how many waves are here? 1, 2 and almost 3. Now here how many waves are there? 1, 2, 3, 4. So that means there is a difference of path between the two waves. There is a path difference of lambda here between the two waves. So this is the difference that we are finding out. How can I find out the difference? By dropping a perpendicular, right? For that, I have dropped a perpendicular here. I have dropped a perpendicular here, which I name it as M, right? So the path difference between the two waves is S2P minus S1P, because this is the longest distance that the wave is traveling and this is the shortest distance that a wave is traveling. So the path difference between the two waves is denoted by del x, which is equals to S2P minus S1P. Now we have already found out the condition of path difference for constructive and destructive interference in the previous class. Then we'll apply that condition here. But very first we'll find out S2P minus S1P. For that, to find out S2P, what I'll do, I'll take up a right angle triangle S2PB. In S2PB, in triangle S2PB, I can find S2P as S2B square plus pb square. That is by Pythagoras theorem. S2p square is equals to this. That is S2p is equals to, S2b is how much? S2b is d, that is d square plus pb. pb till here it is x. Now x plus d by 2. It would be x plus d by 2 the whole square, whole to the power of 1 upon 2. Right? Now, what I'll do is that I'll take out this d square common. As I take d square common, since it's within root, it would be only d outside. It is 1 plus 1 upon d square x plus d by 2 the whole square, whole to the power of 1 upon 2. Now, since this is d square, when I divide it, d is a large distance as compared to x and d by 2, right? So, this term is divided by a greater denominator, because of which the whole term becomes very, very small, so that I can apply binomial theorem. By applying the binomial theorem, I would get d into 1 plus 1 upon 2d square into x plus d by 2 the whole square after the application of binomial theorem. Similarly, I can find S1a. So, S1 p square is equals to S1a square plus a p square, right? That is S1p is equals to S1a is how much? It is d square plus, what is AP? AP is equals to x minus d by 2 the whole square, right? That is S1p square, S1p is equals to d square plus x minus d by 2 the whole square, whole to the power of 1 upon 2. Again, I'll take d square common, d common, that is d square. When it comes out of the root sign, it will be d. 1 plus 1 upon d square into x minus d by 2 the whole square, whole to the power of 1 upon 2. That is, again I will apply the binomial theorem, according to which 1 plus 1 upon 2d square x minus d by 2 the whole square. This would be the result for S1p. After substituting the value of S2p and S1p, what do we get, children? S2p is d square into 1 plus 1 upon 2d square, it is d into 1 plus 1 upon 2d square x minus d by x plus d by 2 whole square minus d into 1 plus 1 upon 2d square into x minus d by 2 the whole square. This is what we get. So that when I open it up, again d becomes common. I'll take it out. It would be 1 plus, d becomes common from both, right? 1 plus 1 upon 2d square into x plus d by 2 the whole square minus 1 minus 1 upon 2d square into x minus d by 2 the whole square, right? Now I'll open it up. I'll get d plus 1 upon 2d into x square plus xd plus d by 4, d square by 4 minus d minus 1 upon 2d into x square minus xd plus v square by 4. This is what we get. Now again opening up, d gets cancelled, right? 1 upon 2d, and taking it out common, what do I get? X square plus xd plus d square by 4 minus x square plus xd minus d square by 4. This is the term that is left out. Now again cancelling it up, d square by 4, x square. So what are we left with? 1 upon 2d into 2xd. That is, 2 gets cancelled. You are left with xd by d. This is the path difference between the two waves. Now, after getting the path difference, as we already know, the condition of constructive and destructive interference will apply that up here. For maxima, the path difference as del x is equals to n lambda. The path difference was x d by capital D is equals to n lambda. Now n is n where n is equals to 0, 1, 2 and so on. Now x is the position on the screen which we have already shown it up in the figure. Now when n starts from 0, I'll get the first position on the screen, that is when n is equals to 0, I would get x0 is equals to 0. Right? That is the first position which is called as the central maxima. It is called as the central maxima. Then when n is equals to 1, I would get the first maxima on the screen, which is x1 is equals to x1 is equals to lambda capital D upon small d. This is the first maxima. This is known as the first maxima. Now when n is equals to 2, I would get x2 is equals to 2 lambda capital D by small d, which is the second maxima. Similarly, I can find out all the maximas, right? Now, when I want to find out the fringe width, that is the distance between two consecutive bright fringes, So, fringe width, which is denoted by beta, is equals to x2 minus x1, which is equals to 2 lambda capital D by small d minus lambda capital D by small d, which would be equals to lambda capital D by small d. This is the expression for fringe width that I got for brightness, that is a bright fringe. Similarly, for a minima, as the path difference for minima or darkness, as the path difference is delta x. What's the condition? The condition for minima is 2n minus 1 lambda by 2. This is a condition for darkness. As you had already derived for delta x, that is delta x is equals to x d by capital D. Right? Now, I will find out the fringe width in case of a dark fringe. Now, for that, I'll equate both of them. XD by capital D is equals to 2n minus 1 lambda by 2. Now here n would be starting from 1 because the central one is already bright, so n cannot be 0. So we'll start with where n is equals to 1, 2 and so on. When I substitute the value, I'll get x, I'll take it as x dash, that is x dash d by capital D, x1 dash I am putting. For n is equals to 1 I am putting, so it would be 2n is 2, n is equals to 1, so it would be lambda by 2 for n is equals to 1, right? As I substitute the value again, what do I get? x1 dash is equals to lambda capital D upon 2D. Yes, lambda capital D upon 2D. This is the value that we are getting. This is the condition for first dark fringe. Similarly, I'll find out for the second fringe. That is for n is equals to 2. For n is equals to 2, when I substitute it, I would get x2 dash small d by capital D is equals to 3 lambda by 2. That is x2 dash is equals to 3 lambda capital D upon small d. Right? Now, I have found out the first dark fringe, I have found out the second dark fringe. This is the second dark fringe. Now, to find out the fringe width, that is the distance between the two consecutive dark fringes, fringe width beta is equals to 3, that is x2 dash minus x1 dash, which can be written as 3 lambda capital D by small d minus lambda capital D by 2D. Right? As I solve it, I'll get 2 lambda capital D by 2D, which is equals to beta is equals to lambda capital D by small d. That is, children, when we derive, when we see both the conditions, in both the conditions, whether it is a maxima or a minima, when we derive the fringe width, it remains the same. That is, in an interference pattern, the distance between the two consecutive bright fringes or the distance between the two consecutive dark fringes always remains the same.